So hi everyone, we have Professor Biswa here. Uh, he works in the area of hardware security, especially the architecture, microarchitecture security. And he earlier was a faculty at IIT Kanpur. And prior to that, he has done his PhD in hardware security from IIT Chennai, Madras.
No, PhD was not on hardware security.
But okay.
Yeah.
What was it in?
It was on architecture, but not on
No, no, no.
security. Yeah.
So, yeah, we will be covering or taking a session on architecture security, which also will have a follow-up lab session. So, welcome and can proceed.
Sure. So, yeah, so welcome again from my side. This is last but one day for the winter school. So, we have the school, but we don't know where is winter, right? Especially if you are coming from northern part of India, right? So if you look at this slide, the definition of winter is 20 degrees. That will happen on Sunday post this winter school, okay? So you can stay here if you want to enjoy the winter after the school. Anyway, so before I start, this will be the protocol for next 5,400 seconds, okay? So I will have multiple pause or what I call break. Otherwise, this is an afternoon session and all of us know what exactly happened, right? Okay. So the goal is not to teach anything and everything about architecture security. The goal is just to develop some bit of curiosity. If you get an alpha factor into your curiosity, then yeah, my job is done. And last but not the least, feel free to email me, ping me, and Sumon is here who will take your lab session. So he is an MS student working with me. So you can reach out and ask questions during or even after the winter school. Okay. So let's get started then. So how many of you know what is architecture? Random answers are okay. Wrong answers are really fine. No issue. Go on. No need to say I want to answer. Yeah.
So how the computer is designed and how its internal working consists, like how is the hardware component?
Hardware components. Anyone else? Uh-huh. Structure of what? Structure of mobile phone? No. This side?
Architecture is like planning.
Planning? Oh man. Okay.
You can have some house architect.
Okay, let me define computer architecture. Okay.
Computer architecture is,
Planning about computer.
yeah, I mean the chips, how you design it so that you can get this software.
Uh-huh.
run it or something.
Uh-huh.
Structure of transistors.
Transistors, come on man. Transistors, huh? I can't hear you.
It's just blueprint, whatever we are going to place on.
Okay, I heard the buzzword blueprint. Okay. Any other answers? No? Who is answering? Huh, go on.
The base design of how the system is to be oriented and implemented.
Okay. Any other answers? All the answers are wrong, by the way. Okay, so don't worry. Anything else? Huh? Internal linkages. Okay. Like genome sequencing? No? What else comes to your mind when someone says computer architecture? You have taken a course on computer architecture, all of you? Yes? Oh, okay, good. Yeah. So have you seen this kind of chips?
Yes, sir.
Okay. So this is an Intel chip, if you want to see it properly. Okay. So someone says transistor, someone says planning, someone says organization, blah, 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 right? Okay, so we are not going to deal with anything else, like all these keywords that you have explained. Instead, we'll actually jump into, oops, okay. we'll jump into this interface that someone has mentioned, right? Some linkage, something. So when you write programs, at the end of the day, the programs are getting executed by some black box. Let's say this is the black box, and it does it so intelligently that your heavy programs get done in few seconds, right? Before you realize it's done, right? Sometimes milliseconds, microseconds that you can't perceive also, right? But then I'm talking about security, right? We are in a security winter school, so why should I deal with what is happening inside a processor or inside architecture or microarchitecture? So the theme for today's talk is whatever industry or research community has proposed in last 30-40 years to improve our performance or our applications performance. Now they are the primary factors for security, right? So for example, if someone has proposed a solution in 1980 saying, okay, try this idea, it will improve your performance by 2x, right? So you take it, Intel will take it, AMD will take it, right? So, but now if you look at that idea is actually causing information leakage, okay? So what I'm showing here in this slide is something called microarchitecture, which is not visible to programmer. As a programmer, you can't touch, you can't see. Have you heard about caches, memory and all, right? So as a programmer, you can't say that, okay, go and touch cache line number 10, cache line number 12, or whatever, right? These are all inside this magic box, but you don't have an interface that can give you direct access to them, right? You can write programs which will use it and it will improve performance, okay? So that's why this interface is pretty crucial. So you have the notion of ISA and registers that you can use in your program, but below that there are so many technicalities that you can't directly access them, and those are microarchitecture, okay? So all of you must be aware of these three terms. Yeah, so I should not go for it, okay. So have you looked at Intel inside logos or advertisements?
Yes.
Right? Everyone must have gone through that, right? So from last few years, those advertisements have been transformed into various attacks inside, okay? So now previously, when someone says Intel inside, it's actually for its performance. It gives you, faster execution time when you run your program. But now in this session, we will see how, attacks can be made on any commercial processor, not only Intel, but most of you use Intel, so I'm using the, using the word Intel specifically. Okay, so these are some of the media articles. If you are following this field, then you must be aware of it. If no, it's completely fine. So this is a new area where, every few weeks you will see a new attack, okay? And these attacks try to steal data in various ways, okay? We'll try to give you a 10,000 feet view about most of the attacks, but not all. Okay, so with that, let me start with something called what is called a cache hierarchy. How many of you are aware of it? Only 10. What about others? Have you heard about caches?
Yes.
Okay. So when I say hierarchy, it's a hierarchy of caches. So instead of only one cache, you have multiple levels of cache. So typically in a modern processor, you will find 3 levels of cache, okay? And so these are actually microarchitecture units which are sitting in between your processor and memory. So why we need cache? Faster access, okay, go on. Yeah, give me answers. What else? Save time, faster access, same, right? Huh.
Temporary storage.
Temporary storage, okay. Again, wrong answers only. Huh. Go on.
Less use of main memory.
Less use of main memory, what will you get out of it?
Less use of power.
Access time is higher than cache access.
Okay, so what's your name? Suman. Okay, so yeah. So Suman said that memory access time is higher, so you should have a cache which will cache some data, and if you get the data from the cache, then it is faster. That's the deal. Why does it work?
Because it keeps the most recently,
most recently accessed data.
So there's that principle that if a data part has been, like, data has been accessed, there's a high probability that will be accessed again.
Okay. So it seems that you have done your architecture course properly, or you have gone through some of the notes properly. Okay. So let's assume there is no cache in the system, the chip that I was showing you, right? Let's say there is no cache. Then what will happen for every request? So every time you write a program, your processor will actually send a request to memory, right? It will take, let's say it takes hundreds of cycles. Okay. The notion of cycle, if you don't understand, just say that 100 units of time. Okay. So now if you put a cache here, the hope is whatever I have brought into the cache, it will be useful. And the rationale behind that statement is there is some locality that exists in our programs. Right? If you are writing something inside a loop, we are accessing the same array or the nearby array elements, right? So if I bring the data into the cache, then there is high probability that I will get the data from the cache. So that hides the latency. Okay, and it's actually basically a prediction technique, and this prediction works because we have locality. If your application doesn't have locality, then this won't work. Okay, fair enough. Now, all the systems that you see in modern computing world, right? They are multi-core system. Even your mobile phone has 4 cores, 8 cores. Everyone understand that, right? Before buying, you check that, right? Okay. So what's the utility? So the utility is you can have multiple applications running together, and when it comes to the cache hierarchy, now each core or each processor will have its own caches. Okay. The chip that I was showing, that's actually a multi-core chip. So within that chip there are multiple cores. Okay. But there is a cache level which is actually shared by all the cores. Okay. So there are some caches which are private to a particular core, but there is a cache and there is memory also which is shared by all the cores. Okay. Any questions so far? This is the first pause. Louder.
In the last slide,
Huh.
I could say that
Sorry. Yep.
the previous one, where the RAM was very far away.
Okay, this one? Huh.
If you just put the RAM closer,
Huh.
would that be helpful?
Okay, let me show you a RAM. I think I have it. This is actually, it's called DIMM technically, but for undergraduate architecture students, it's okay. You can just call it a RAM. As you can see, this is a different device altogether, right? So it is not coming along with the chip, the processor chip, which means it has a different slot where you have to put it, and the processor has to communicate with the memory through those slots, right? So we don't have a solution for the problem that you said, right? You said, can we move it? We can't move it. Okay? Yeah. Go on. You can just call Biswa, no need to say that.
That's why are the Apple new chips like M1 chips are faster. And
That's why, meaning?
like the distances come. Yeah, it includes the RAM inside it.
Mm-hmm. It doesn't include the RAM inside the chip. You can't.
How is that like different from Intel chip?
No, all the chips that I was showing you, they are having processors and caches. They don't store the memory. Memory is a different entity altogether. Okay. So if you look at in terms of companies that design DRAMs, let's say companies like Samsung, Hynix and all, so they design DRAM chips. Companies like Intel, AMD, Apple, they design their processors. Right? They're like two different companies. And that's why they are designed independently. Okay. Any other questions? No? Okay. So let's move. So we'll jump into what is called side channel and covert channel. So yesterday Debdev talked about hardware security. Did he mention about side channels? Yeah, can someone tell me what is side channel? I hope like all of you have lunch, breakfast, everything. You have enough energy to speak.
So we are
Huh.
side channel attacks, we are the adversaries is overseeing the communication between the victim.
designing some cryptographic algorithm.
Forget about cryptography. They just
Mathematically,
forget about mathematics.
yeah, but when we put it on system, we can from the voltage or
You are going too deep actually. Give me a simple example that you can see in your day-to-day life.
The communication is
Communication? What?
so the information which is being communicated that is
So I am giving you information. It's a side channel?
no sir.
No. Okay.
So relay information from electromagnetic radiation.
So only if it is electromagnetic radiation then?
Sir,
Then?
electricity also.
Things like timestamps or anything.
No, so those are different, medium, right, through which you can, yeah. But what exactly is a side channel or covert channel? Okay. So how exactly the leakage happens?
Because the designer did not consider all the algorithms, like
Hang on.
the designer that made the whole channel, he did not consider some of the cases and algorithms, and the leak occurs due to that.
Okay, so the conclusion is the designer didn't consider all the possibilities through which information can be leaked. That's why it happens.
Yeah.
You are saying something.
I was saying it's not direct, it's indirect.
What is direct, what is indirect?
I mean, while designing these algorithms, we might not have considered about these types of algorithms.
Okay, ठीक है. Let me, in the interest of time, let me jump into it. So let's start with covert channel. So covert channel is actually not an issue per se. If you look at the so-called definition, it says it's an intended communication between two or more parties. Okay, but the key here is communication should not be possible. For example, let's say there are two applications running on your mobile phone. As per the system semantic, you have gone through the system security session, right? Let's say as per the OS, right? Those two processes should not communicate, but still they are able to communicate, right? So it's a covert channel. But it's intended because both the parties know that they are communicating. Okay? So this is one of the examples that one of my students gave during a lecture. So for example, if Gmail, WhatsApp, everything is blocked in your country, but somehow YouTube is still alive, right? And you want to communicate something to your friend, you can upload videos on your YouTube and say that, whenever I upload something, then this is the message that I'm trying to send, right? If you are uploading a YouTube video, then it's 1. If you are not, then it's 0. So you can communicate a string of ones and zeros just by uploading videos on YouTube, right? So side channel is actually a security threat where it is unintended, So if you have multiple parties sharing a system, in side channel, you are actually causing an information leakage where the other parties, they have no information about it. They are not aware of it. Is this clear? The notion of side channel and covert channel? Okay. So side channel is, let's say there is a crypto library running on your system, okay, and the semantics are still the same. As per the OS semantics or the system semantics, communication should not be possible. But the crypto library doesn't know that there is someone else is trying to steal my secret key, right? But in case of covert channel, it's actually intended. The other application has knowledge that, there is another application who is trying to send information to me. Is this clear? Okay. So you must have heard about inter-process communication or inter-app communication, right? In your OS course. Does this ring a bell? Yes? No? Yes? Okay. So inter-process communication is actually, it's a valid communication, right? Like one process is trying to communicate something. You must have heard about, socket or anything, right? Any medium through which two processes are communicating, right? But here, the scope is that, the overall system semantics doesn't allow you to communicate, but still you are able to communicate. Okay? So let's try to create a covert channel through cache. Everyone understand cache, right? If not cache hierarchy. So cache is a black box which is sitting in between your processor and memory, and the goal of the cache is to make sure the average memory access time is less. Okay? Have you heard about the notion of sets and ways? So cache memory is actually organized as few rows and columns, So the rows are known as sets and the columns are known as ways. Okay. If you don't know, it's completely fine, no issue. Okay. So now two applications, they want to communicate, okay, by a covert channel, and the covert channel will be cache. Okay, cache will be a covert channel. Okay, so let's see. So let's say these are the two processes, process 1 and process 2, and what they are doing is pretty simple. So they are accessing a particular set in a cache. So as I mentioned, set is nothing but a row in a cache. Okay. So let's say you write a for loop, and that for loop makes sure that you send requests to a particular set in the cache. Okay. And you do that within a for loop. Continuously you do that. Okay. So now if this guy wants to send 1, right? So every time it will go and populate this particular set. Okay. Are you with me so far? Now the receiver, what it will do is, it will try to do the same thing. Okay. It will go to that particular set and try to access, right? But since it's a shared resource and it's a limited size resource, which means if one guy is putting, let's say, information for 4 different cache blocks or 4 different memory addresses, and if other process comes in, then those 4 addresses have to be kicked out. Okay. So now what this guy will do, this guy will actually try to access the same set again and again, and if it takes more time to get the data from the cache, which means someone has actually stored something here, because of which it kicked out whatever this process has stored in this cache. Are you getting me? So it's a shared structure where two processes wants to communicate some information, okay, and the receiver actually tries to see whether it is able to finish the accesses faster or slower. So it can be a simple array access inside a for loop, and you put a timer and see how much time it takes to finish the array access. If it is taking less time, that means process 1 hasn't sent anything. If it is taking more time, which means process 1 has sent something. Is this clear at a high level? Okay. So in a normal communication, you would have done that. You would have written a socket programming when process 1 will actually send some information to process 2, and process 2 will receive it, right? But here, instead of using the inter-process communication mechanism, you are actually thrashing the cache, or you are creating pressure on the cache, right? And based on the cache, you are communicating, based on the cache state, you are communicating information. Is the difference clear? Question?
You said that if sender is not sending something, then it will take less time.
Yeah.
So why is it?
Yeah, so because, let's see. Yeah, if sender is not sending anything, that means receiver, whatever receiver has brought into the cache, right? It will be there, right? No one will kick it out.
Okay, so receiver has put something there.
Yeah. Both of them are actually trying to access. So if you look at, right, this guy is trying to fill a particular set I, and even receiver is trying to fill the same set I. Okay. So if sender is not coming in between, then whatever receiver has access, it's there in the cache. So it will be faster. But if sender has come in between, then it will kick it out, the data that receiver has brought, right? And because of that, receiver will take more time.
So the socket code, that is not, why is this not that a covert channel communication?
No, that is, you are telling operating system that, yeah, we are communicating. Operating system is the, let's say, boss of the system, right? Which gives you all the isolation boundaries, whether this process should talk to other process or not, right? Through socket programming, you are telling OS that, okay, I will say hi to process 2.
So intended communication was only required, or
That is intended communication, but if you have looked at the initial set of slides, right, for covert channel, the scope was the OS semantics or the system semantics doesn't allow you the communication, right? Then only it becomes a covert channel. Yeah. Question?
Sir, is this like a locking sort of mechanism?
No, it's not a locking. No. So just assume there is a for loop here. Okay. So this guy is keep on sending requests to a particular set. This guy is also accessing the same set within a for loop, right? And it will measure the time it takes to access that particular set. Okay. So both the things are happening concurrently, right? So if this guy doesn't disturb the content of this set, then this guy will get cached every time because no one is disturbing, right? If this guy comes and disturbs, which means this guy will kick out the data that was brought by process 2. Next time when this guy tries to access this set, it will get missed. It's just a game of hit and miss. Okay? If someone is interfering with you, then you will get misses. If no one is interfering, you will get hits. Hits meaning faster access, misses meaning slower access. Okay? That's why it's called a timing channel. You are exploiting the timing difference. Okay? Clear? Any other questions? Okay, so let's move on. So we discussed that previous scenario as a covert channel where there were like two intended parties were communicating. So if you want to convert a covert channel to a side channel, now you can convert this, sending 1 or 0 into a secret message, right? Well, this is not intended. You are trying to, infer. You are trying to guess what is happening with the other process, right? And the other process has no clue. This is the difference, right? So that's why instead of 1, I have put secret here, which means it's a information that should not be leaked, and through covert channel you are leaking it. Okay, but the protocol is still the same. The victim will come and access the cache, then the attacker will again try to access the cache. If it gets a faster access time, it will know that okay, no one has accessed the cache, right? So based on that, it will know. We'll see that. Okay, have you seen this code snippet? Did Devdev talked about it? No? Yes? Yeah, square and multiply. Yes or no? Yes. So all of you understood it? Can someone summarize in one sentence? All of you said yes. Go on.
If we have 1 is the bit state,
Mm-hmm.
so bit can have 1 or 0.
Yeah, bits can have ones and zeros. Yeah.
1 then you square and then multiply. If you have 0 then just square root multiply.
That I can see.
Sir,
Yeah, sir is here. Don't worry. Go on.
sir, if the if statement is executed, then the time taken would change, and
No, forget about time taken. We will jump into code channel, side channel later. I'm just saying what exactly is this particular code snippet doing. It is anything fishy here. If yes, then why? If no, all good. You can sit silently. We got to know the bits based on if and else statements. Okay. So in computer architecture terms, these are actually called control flow or data flow, right? Control flow meaning if this condition is true, then the program actually enters into this part of the program. Okay. If not, then yeah, you jump out of this code and then do something else, right? So if you remember your architecture lecture, you must have heard about your processor fetches instructions sequentially 1 by 1, 1, 2, 3, 4, 5 like that, right? So that's the control flow. And whenever you get a if condition or a for loop, you jump here and there, depending on the outcome of the condition. Okay. So now the culprit here is these conditions. If I remove the if statement, then there is no issue, right? Is this correct?
yes, sir.
If I remove this if statement, then I won't be able to make this deduction, right? That okay, a particular bit of exponent E is 0 if it is entering into if or if it is not entering into if. Pretty straightforward, no big deal, right? Okay. So now if this is the case, how will you attack? This is part of crypto libraries, famous ciphers, they have this part of the code, okay? So how will you get this E by doing a cache attack? What should you do? This is a question, so I'm demanding answers.
Sir, if the bit is 1, then the multiply part will also be there. And
That is clear, that is clear. No, so the deduction is if the bit is 1, then it is doing square, reduce and multiply and reduce. All 4. If the bit is 0, then it is doing only square and reduce, it's not entering into the multiplication. That is clear, right? Now I am asking you, we just discussed the cache covert channel, right? How to create a small covert channel. So can you design a covert channel which can leak the values of E or the different bits of E, the string E?
You can see the time taken for when it changes the bit, break the for loop, whatever.
Let me give you the setup. So let's say this is a crypto library that is running in your system. Okay, so you will do it as part of your lab session after my talk. So let's say this is running. Okay, you need to write a code which will give you the information about E. This is a different attacker process. Is this clear? So here the victim is the crypto library, and the crypto library has this code snippet which is running on your laptop. Okay, you should write a program exploiting the cache timing channel which will tell you, okay, these are the bits of E. Yeah, what should be the approach? Timestamps. See, this is a different program. You can't enter into the crypto library ka program. So you are a different process. The crypto library is a different process. The only thing that you can do is you can send request to cache, right?
Can observe the timings of the process right now when it is.
Yeah, obviously it's a timing channel, so you'll observe the timing. But how? What exactly will you observe?
One part is multiplying x into x, another is x into. So, I mean, the cache has to fetch e if it is doing some multiplication, otherwise it will.
Okay, so when you look at all this square, reduce, multiply, reduce, right? Eventually they will be in the cache, right? Yes, no? Are you able to make a connection? I'll take your question, just hang on. So all these functions or all these operations, right? Square, reduce, multiply, reduce, they are actually there in some part of memory address, right? And you will actually cache it. Clear? Okay. You had a question.
I was hoping you were able to answer the question first, how will the attacker.
Yeah, go on.
So I wanted to clarify, these are two separate processes and they don't know when one process starts and when the other.
No, let's make it simple. Let's assume that the crypto library is running 24/7. Okay.
So we just keep calling the cache.
Yeah, you have to keep sending requests to cache. You can't call cache because cache is not a software data structure, right? So you have to send some request to the cache which can disrupt the crypto library ka behavior.
So we just keep calling the cache and hopefully we get some information.
Yeah, hopefully that's the approach, but I'm expecting a bit of preciseness. So let's see. Okay, can you spend few seconds looking at it? So can I assume that this is a crypto library? Because we discussed, right? Based on a control flow dependency, there is a different path, right? So let's assume if this particular secret bit is 1, then you access a particular memory address, otherwise you don't. Okay? So now as an attacker, you can do this. You can flush this particular address A. So the semantics of flush is, this is an instruction, okay? So in Intel x86 there is an instruction called CL flush, cache line flush. So if you say go and flush this address, it will be kick out from the cache hierarchy. It will go to the memory, okay? Which means every time you execute this instruction, it makes sure that this address A is not there in the cache. Okay, now can you design the protocol for inferring the array E? Is the notion of CL flush clear? So CL flush takes a virtual address which is visible to the programmer. As a programmer, you can say that, okay, go and flush this particular variable. So then it will go to the cache and it will make sure that that particular address is not there in anywhere in the cache, not even in L1, L2, L3. Okay, so which means after you flush, if you try to access that address, you will get a miss. Is that clear? Okay. So now if that's the understanding, how can you create a side channel to get the information about array E? Sorry?
We flush a bunch of spaces in cache so that only a few are remaining, and then where the space is left in the cache.
Okay, I think that's a valid approach, but let's make it simple because we are running out of time. So it's a crypto library, right? So even you can use that library, right? So your crypto library is a process. Whenever anyone tries to use the crypto library, that crypto library ka accesses will be part of your accesses. Yes or no? It's like a shared library, right? Let's say multiple users are doing bank transaction on a given system. All of them will actually call the crypto library, right? But the code of the crypto library is the same, right? The code snippet is the same. Okay. So the flush based mechanism that we are discussing from last 5 minutes, the high level answer is you flush out all the addresses of interest. What are the addresses of interest? The address for square, the address for reduce, the address for multiply. So as an attacker, you flush out all those addresses, which means you are making sure that those addresses are not there in the cache. Is that clear? Now the victim is running or the crypto library is running, right? If it is running, it will bring those addresses into cache, right? So if it brings, then what you should do is you should again try to access that particular set of addresses. And now if you get a hit, it means that the crypto library has brought those addresses, right? And depending on for which addresses you got a hit, you will know whether it's a 1 or 0. Is that clear? At a high level, let me give you the actual attack. So the y-axis here shows the latency or the time units, okay, when you try to access all these addresses. The x-axis is showing the different addresses. Address correspond to S, R, M and R, square, reduce, multiply and reduce. Okay. Now if you look at here, there are certain iterations where the time or the latency is actually higher. Why is it so? Any guess? Come on, this is pretty straightforward. Okay, the question is the attacker is actually flushing these addresses from the cache, and then it is again reloading, again sending requests to those addresses. Sometimes it takes 100 cycles, sometimes it takes 300 cycles. Because the cache is clear, right? Yeah. So which means there are instances where there is no occurrence of these addresses in the cache, and there are cases where the addresses are actually present. So the addresses, so the cases where the addresses are present in the cache, it means that someone has actually brought in because I have flushed it. Because if I have flushed the addresses from the cache and still I am getting hits, that means someone else has actually brought in. That's clear, right? And so let's say you have a threshold in terms of time. Anything less than 100 is actually a cache hit. Anything more than 100 is a cache miss, right? So what you will do, you will look at all these iterations, and based on that you will be able to deduce that okay, this part is S and R, then SRMR. Based on that you will be able to create the zeros and ones. Is this clear? This is called flush and reload attack. It's the most simple or the simplest attack in microarchitecture security. Okay. So there are other attacks that we will see, but if you look at the crux of all these attacks is this particular statement: cache miss takes more time than cache hit. So you can actually create a timing channel out of this behavior. Okay. So let me just quickly give you the flush based attack again, but before that I will take a pause and take questions. Is the protocol clear? Flush reload attack. You are flushing the addresses, making sure that those addresses are not there in the cache, and then still if you are getting hits, it means that someone has bought into the cache. Okay, that's the protocol. Question.
So why do we need to flush all the addresses?
Not all the addresses, only those addresses.
Like the else and if both the conditions we have to flush?
It depends on what you want to achieve, right? So here you should flush the addresses that store this particular square, then reduce and then multiply. These three.
What if I only flush the last one?
What do you mean by last one?
The middle one.
Yeah, if you flush only this one and probe, then you will be able to infer about ones, but yeah, that is with the assumption that you know the entire flow. Okay, it can happen that maybe the other part is about 2 or 3 or 10 or 100, right? So here it's a pretty simplistic example where you can do that, whatever you just suggested, right? You can just probe on this, and based on that you will know the ones. But I'll give you a more finer, subtle issue. If you know the number of ones, but you should also know where are zeros, right? So let's say if my key is 256 bit, and through your version of attack, you will know that okay, out of 256 bits there are 100 ones. Where are those ones? Which bits? So here if you do both, you will know where are the zeros, right? Then only you will be able to get the entire key, right? But that itself is an information, right? If I can say that okay, out of 256 bits, 100 bits are 1. So you have reduced the search space, right? Now you will actually try to find out the rest 156 bits. More questions?